Hello everyone, my name is Hussein Marah and I am a PhD student at the University of Antwerp, Department of Computer Science, and as a part of ANSIMO COSI Core Lab. And today I'm going to talk about our current research project with a title Intelligent Agents and Multi-Agent Systems for Modeling Smart Digital Twins. First of all, I will start my presentation with the contents. I will talk about system structures, what is an agent, characteristics of agents, multi-agent systems, and example of multi-agent system working practice. And of course, we will talk about digital twin as a core topic in our research and the challenges and roadblockers of digital twin. And I will talk about the proposed framework, MADTwin, and we will show a case study and we will show some demonstration videos, and we will conclude our presentation with the challenges and future work. In our time, we are witnessing a significant change in various disciplines of our lives. This change is driven by digitalization and smart technologies, and specifically in the domain of industry and manufacturing. Digitalization is prepared by uh, so-called fourth industrial revolution, Industry 4.0. Industry 4.0 introduced new concepts, approaches, and methods to build industrial solutions. And as you can see, we have two structures. The first one for Industry 3.0 and the second one for the Industry 4.0. In the first structure, we have centralized monolithic structure, and we have hierarchy-based communication between layers. While in the second one, we have flexible systems and machines and functions are distributed through the network as the structure is more decentralized and distributed. And this is what we want to achieve with the Industry 4.0. To achieve such digitalization in systems, one of the promising approaches is agent-based paradigm, which has been adopted in industry and manufacturing. So what is an agent? In the literature, there are a couple of definitions that have been given to software agents. As you can see, early experts of this domain gave their definition according to their perspectives. For example, Waldridge and Jennings said an agent is encapsulated computer system that is situated in some environment and is capable of doing flexible and autonomous actions. Russell Norweg said agent is something autonomous that perceives and acts in the environment. And of course, what is common in those definitions is that agent is autonomous entity and can perceive and act to the environment, and of course can cooperate or can communicate with other agents. From our perspective, agent is an autonomous component that represents physical or logical element in the system, and this element is capable to act and achieve its goals and of course interact and cooperate with other agents. If it doesn't possess the enough knowledge and the skill to reach its object. As an example here we have this agent and this agent has sensors and effectors or actuators, and the sensors perceive the environment and the actuators act or affect the environments. As more concrete example, here we have this robotic arm and the agent controls this robotic arm, and we have this loop of perceptions and the actions where the perception can be the pressure value and the actions can be picking up or not picking up according to the measured values. Features and characteristics of agents. can be enlisted. As you can see, the first one is autonomy, which is the capability to take their own decisions. The second one is the cooperation, which is the ability to cooperate with other agents in order to solve the internal goals or the common goals of the system. And this goal can be complex and the individual agent cannot handle alone. Intelligent characteristics of agents, according to Waldridge and Jennings, is the reactivity, which is the perception of the environment and the quick responses to those changes or modifications, and the proactivity, which is the ability to take the initiative. And of course, the social capabilities, which is almost like the cooperation and the communication. So agents can cooperate, interact, and communicate with other agents in order to solve certain problem. Other optional properties of agents which can make the agent more intelligent is the mobility and the reasoning and learning mechanisms. One of the key features of agent approach is having a group of agents cooperating with each other to solve a complex problem which cannot be solved by an individual agent. According to this concept, there is a need to have a framework or an environment to manage, organize, and orchestrate those agents. Thus, the idea of mass or multi-agent systems has been born to tackle such a problem. So, basically, multi-agent system is a framework to organize and manage a group of agents or society of agents. And multi-agent system approach or field is derived from distributed artificial intelligence. Here, as you can see, an example of mass working in practice. In this figure, we have several agents which can communicate with each other, and every individual agent has a specific or certain goal to achieve. And sometimes this agent cannot handle or achieve its own goal unless if other information has been provided from other agents. So that's why we need to communication and cooperation between agents to solve a big and more complex problem. Here in this table, we try to make a comparison between conventional approach and multi-agent system approach. As you can see, there are a couple of metrics which can differentiate the conventional systems from multi-agent systems. For example, hierarchies of large programs, while in a multi-agent system we have large network of small agents, and the execution of operation in the conventional approach is being executed sequentially, while in the multi-agent system agents can have parallel operations and the instruction from top to bottom, while in multi-agent system we have the negotiation concept between agents, and of course the centralized decision in conventional approach, while in mass we have distributed decisions according to different agents. And of course, all those characteristics can differentiate and make multi-agent system as a promising and different approach to solve complex and distributed and have a large scale flexible system. As a conclusion from what we introduced and discussed about multi-agent system features, agent paradigm can be used to solve many problems and issues, to build a complex and large scale system by having intelligent features such as proactivity and autonomous behavior, and of course distributed architecture and thinking, where a complex problem can be divided into several small problems and solved individually by agents. And of course we can achieve pluggability and reconfigurability by doing the changes on the fly and adding agents or new agents to the system without the need to shut down the system. And of course this architecture can achieve the load balancing by distributing the load among the agents, and we can have of course modular system where building the system is done by adding pieces like using Lego bricks. And of course we can have a scalable system which can be extended and new agents add incrementally. And lastly we can have robustness, which means if an agent or a decision has been failed, this cannot cause or doesn't cause a failure of the whole system. In this slide, we try to give an example of mass applications. And as an example, we have a project with a tighter integration of process and quality control using multi-agent technology, or what is called the GRACE. And this project has a main objective, which is realizing a cooperative multi-agent system operating at all stages of manufacturing system. This project received funding from European Union with 2.5 million, and it has an overall budget about 4 millions. And you can access to these projects and check the details and the results of these projects through this link provided below. Following the GRACE project, as you can see here, we have an architecture of the system or the proposed solution that has been used in that project, and integration of the quality control and process has been achieved in order to improve the efficiency and the quality, and of course the customization of the manufacturing system. And basically a multi-agent system has been used to collect the data and perform real-time data analysis and correlate operating variables. Another example of multi-agent system applications, we have another project called Goodman with a title Agent-Oriented Zero-Defect Multi-Stage Manufacturing. And as you can see in this highlighted text, the main idea of Goodman project is to integrate and combine process and quality control for a multi-stage manufacturing production into a distributed system architecture built on agent-based cyber-physical system and smart inspection tools designed to support zero-defect manufacturing strategies. And this project received a total funding about 5 millions and 4 millions contribution from the European Union. Goodman project has used this shown architecture where they have layers of agents, and every layer is responsible for doing specific tasks. And as you can see, we have the lower or the bottom layer, which is controls the cyber physical system, has been monitoring and operated. And of course, integration of quality and process control in real time has been achieved by using a multi-agent system for data collection and real-time data analysis and correlation of operating variables. Some use cases has been performed in a Goodman project with manufacturing and automotive companies like Zanini and Volkswagen and Electrolux Professional. And of course, you can access all the details about those use cases, and the results have been published through this uh, official project link. As a concrete example and explanation of Goodman project, as you can see in this figure, there are different stages of manufacturing, framing, finishing, line assembly entrance, and final fitting, and all those stages are controlled by agents. And this framework has been implemented using the JIT platform and OPC UA standard. Another example of utilizing multi-agent system in manufacturing by multi-agent system digitizing dimension defined by RAMI. Uh, and in this research with the title Agent-Based Asset Administration Shell Approach for Digitizing Industrial Assets, a physical agent has been combined with asset administration shell to result or to produce Industry 4 component. And of course, every Industry 4 component can communicate with other components through the network, and by utilizing the agent capabilities like sociability, reactivity, and the proactiveness and the intelligence and achieving optimization and collaboration. Yet another example of utilizing multi-agent system in industry has been introduced in this research, where Cosmixer has been introduced, which is a system for mixing cosmetic products. As you can see, some of the requirements has been strongly achieved, like interoperability and virtualization and decentralization, and modularity and openness by utilizing agents. And agents has been used in different stages of manufacturing and mixing processes. In this slide, I will talk about digital twin topic, which is one of the core topics in our research. Digital twin has become a trend in the research, as you may know and have heard about the concept, but I will try to summarize it quickly. Digital twin is a real-time virtual representation of a counterpart of a physical object or a process. The main characteristics of a digital twin technology is the connectivity between physical and digital asset. And this connectivity what makes a digital twin a promising approach. Why digital twin has gained this much attention? The use of digital twin enables organizations to obtain valuable insights related to their products, the physical system, which they can monitor and make accurate prediction driven by the data collected by digital twin. As you can see in this figure, in digital twin, the data is collected from the physical asset, where this data is being used by many tasks and doing like simulation and monitoring and diagnosis and prediction and optimization. And of course, doing all those tasks and procedures can improve the system and its behavior. However, because the high complexity level of digital twin, there are several challenges have been faced while realizing a digital twin for cyber-physical system. As you can see here, we try to enlist and merge the challenges that have been mentioned in the literature, and in the next slide, we try to split those challenges into implementation and performance challenges. In this figure, we try to categorize challenges into two categories. The first one is the performance challenges, where we have the challenge of having intelligent and autonomous behavior, and achieving efficient data gathering and processing, and having a real-time synchronization and communication between physical and digital assets. While in the implementation challenges, we somehow have integration and coupling methods and techniques issues, and we have interoperability and standardization problems, and yeah, we have the challenge of achieving or having high fidelity digital representation. All those challenges uh, represent a roadblocker uh, to achieve digital twin for cyber physical system. Despite all the challenges have been discussed and enlisted before, we try to propose a solution based on agent-based approach to build a digital twin. So the main objective and the contribution of this study is to discover and investigate and explore the potential of utilizing agent-based paradigm to design and build an intelligent digital twin. The features that we plan to have to consider in our digital twin is having reasoning mechanisms and learning capabilities, and of course having monitoring and simulation features, and of course visualizing the system. So our proposed solution is what we call MADTwin, which is a multi-agent digital twin framework for developing and building digital twin. And this slide, the MADTwin architecture is being given. As you can see in this figure, we have two layers. The first layer, the blue layer, which contains all the physical assets and is called agent-based cyber physical system IoT layer. This layer basically contains cyber physical system, which, for example, has a sensor or actuator or other hardware component, and this system is integrated with an agent and is called called a physical agent, and thus physical agent controls all the process and operations of this physical system, and accordingly this physical agent has its counterpart in the other layer or the above layer, which called agent-based digital twin shadow layer, and it contains all the digital assets. So a digital agent is connected to a physical agent and synchronized with each other, and digital agent receives the updates from the physical agents and communicate with other agents to do other tasks like reasoning or learning or simulation or visualizations, or even to restore to store the data in the repository. And as a result, the user can carry out several tasks by using this digital twin, like reasoning and learning and simulation and visualization in order to control and to monitor and simulate the system. As shown in the previous slide, which illustrates the figure of the MADTwin architecture, agent-based cyber-physical system, IoT, which represents the physical assets, is a layer where the physical components and agents are mapped, integrated, and incorporated to work as a single entity called a physical agent. To explain physical agent more concretely, here, as you can see, we have this part which represents the cyber-physical system and the agent or the physical agent, and represented in this robot. And this robot is a physical system, and inside this robot, Raspberry Pi and BrickPi, there is an agent deployed which controls all the process and operations of this robot. So this is called physical agent, and basically those are the technologies that have been used to deploy and integrate agent with cyber-physical system. We have used Jade platform to design and develop agents, and of course Java, and we have used a hardware component as Raspberry Pi and BrickPi to build the robot, and the Lego technology, and of course we have another physical component which is used for localization and navigation, ultra wideband, and which communicates through MQTT protocol. On the other hand, we have the agent-based digital twin shadow, which represents the digital assets, and basically it's the layer where the digital assets are located. And digital assets include basically digital agents, which represents the, or which are the counterparts of physical agents, and other abstract agents such as learning, simulation, and reasoning agents. And of course, other agents can be included in this layer as long as there is a need or there is a service provided by this agent. Following the same concept, digital agent is a virtual representative of physical agent. And as you can see, this part represents the digital agent, which represents the physical agent. And in this layer, digital agent communicates with the other agents located in the same layer. For example, learning agent or reasoning agent or simulation agent, and doing tasks or storing data in data repository. And here some of the technologies have been used and utilized to deploy digital agents such as Python and Qt for building a graphical user interface and having a visualization, and Jade has been used to deploy the agents and integrate them with the physical agents, and of course POSIX has been used to get the data from the tags, the ultra wideband tags, to have a real-time data of the robot's coordinates. In this slide, we try to show and illustrate more concretely how physical agents and digital agents are connected by using Jade platform, and how they are communicating using agent communication language, which is standardized by FIBA, and it's called FIBA ACL. And of course, the agents also use real-time data such as MQTT data generated from ultra-wideband tags to read the coordinates of the robots. And of course, digital agents can use this data to do some monitoring and visualizing tasks, and also this data can be stored in the repository to have it as a historical data. And this digital twin lifecycle represents the stages that have been followed from the design and develop and operate and do some maintenance and upgrade of the digital twin. As I showed before, here we try to explain the agent-based twin monitoring and simulation interface, and this interface represents the visualization interface that built upon the JADE or digital twin to show a real-time simulation of the robots. And as you can see, we have here the physical agents connected to ultra-wideband tag, which generates and sends the coordinates of current tag and send them to the control agent. And in this control agent, simulated agent can be created for a physical agent, and this of course simulated agent represents a digital agent of that physical agent. And of course all those processes can be shown in the graphical user interface to show the physical and the digital agent and how they are operating and moving in the environment. To explain the ecosystem and the framework and how does the simulation works, here we have a concrete scenario of a warehouse case study, and the goals of the case study is that we have a digital twin where we can plan and assign the mission for the robots and monitor the robots in real time, and of course detect any failures or deviation between the path, the real path, and the optimal path of the robot. And of course, the robot should have safety operation and requirements such as detecting obstacles and collisions. For instance, or for example, imagine that or assume we have a robot here and we want this robot to move from this source point to this destination point, and yeah, and this is path represents the optimal path of the robot, or yeah, the path that the robot should follow. And in order to follow this robot, yeah, deviation must not happen. But in reality, we have the opposite due to some other factors like physical failures, or maybe unreliable physical components, like maybe what we use because they are not industry and accurate that much, and yeah, other factors like the environment and so on. So in reality, the robots sometimes follow or deviate a little bit from the real or the optimal path, and follow a real or yeah, an actual path, and the physical agent yeah reaches to this point, while in the simulation we have digital agent, and this digital agent follows the optimal path. And we have done this because we want to know the deviation, or how how much the physical agent deviated from the optimal or yeah, the ideal path. And as you can see in this figure, those points represents robots. For example, we have this robot, and this this robot wants to move from this point to this point to this point, and this robot can, of course, detect obstacles, maybe in the spot, and yeah, of course, collision can be detected by, yeah, or can be broadcast by a high-level agent, which located in a digital twin, because usually robots don't have this information, and physical agent need some like yeah, a high-level perspective of the system, or of all the robots located in the environment. That's why collision detection is being detected in a high level, or in a digital twin level. However, yeah, ultra-wideband tags used to navigate and localize the robots in their paths, and yeah, ultrasonic sensor are used to detect obstacles in front of the robot. In this slide, we are showing the graphical user interface of the ultra-wideband technology, which is provided by the POSIX uh, system or POSIX company. As you can see here, we have the map of our lab, and in this map, yeah, we can somehow know where the tags which are installed in the robots where are located, and we can localize them while they are moving and operating in the environment. In this slide, we are showing Jade platform, and specifically the sniffer, which one of the tools provided by Jade. And by using this sniffer, we can detect, or we can see any messages has been exchanged or communicated between different agents in the system. In this slide, we are showing the graphical user interface of our monitoring and simulation tool of our digital twin, and this tool provides different tabs. For example, we can show the map and MQTT log, and the agent messages, and showing the messages between agents, but simpler than the sniffer in Jade. And of course, we can control and assign agents in this tab, and we have this other settings. And this is the graphical user interface, and showing the map of our lab, and it follows the same architecture as shown in POSIX or ultra-wideband technology. Here we have those colored dots, which represents the ultra-wideband tags which are installed in the robots. So basically, here we have the coordinates, or the position of our robots in the system. In this slide, we are showing one of the features and functionalities of the monitoring and simulation interface. As you can see here, we have two colors which represents physical and digital agents. The blue color represents the physical agents, and the red color represents the digital agents. And in this scenario specifically, we specified two targets, or two destination points for the robot, and the robot should follow this optimal path represented in the red color, or represented in the physical and the digital agent. But in reality, the robot deviated a little bit and moved not that smoothly. As a recap, we are showing the different user interfaces and functionalities provided by MADTwin framework. For example, here we have used ultra-wideband technology user interface, where the tags are showing in the map, And of course, we have used the Jade framework and the sniffer to show the messages exchanged and communicated between agents. And of course, we have the cyber physical system with the ultra-wideband technology and ultrasonic the sensors to detect obstacles and collisions. And finally, we have our design digital twin simulation graphical user interface where we can simulate and determine the deviation level between physical agent and digital agent or simulated agents. So, however, now we are moving to demonstration videos. So let's yeah have a brief explanation of the system. As you can see here, we have initiated the graphical user interface of our monitoring and simulation tour. As you can see, we have 3 robots here, and we have the same number in the POSIX interface, and they have the same coordinates and the positions. So yeah, this represents the POSIX interface, and this. So now we're starting our initiation of the system. The first one we have started is the robot with the address 112. So as you can see, every robot is contained in a different container and is connected directly to the main container, and this takes some time to be connected. Yeah, we wait until all robots are connected to the main container, and then we return to our graphical user interface in order to manage and assign and plan missions to different robots. So yeah, we move to this tab agents, and we can create a dual agent or simulated agent, or basically a digital agent of the physical agent, which will be simulated with the physical agent, and will show the difference or the deviation level uh, between the physical agent and the digital or the simulated agent. And of course, here we could specify or set different colors in order to distinguish between different agents. So now in this interface, we select all the agents that we want to sniff and to detect messages between them using the Jade platform. And now we move to assigning and planning missions to robots. In this, of course, video, we are showing just one point or one destination for every robot. Yeah, we can show or we can select any point in this map and just click on the target robot that you want to reach to this point. So once all all robots are set, we can start the missions for the physical robots, and you can see the robots started to move in the environment for both physical agents and digital agents, as we will see in the end of the video. Yeah, of course. Yeah, and this interface shows the collisions situation that might happen or happened between robots, and of course we can show the acknowledgement messages which represent the completion of missions. Yeah, as you can see here, robots are moving in real time and trying to reach their destination. And of course, as I mentioned before, robots sometimes don't uh, follow the ideal or the optimal path. And that's why we have used this graphical user interface to simulate between the idle path and the actual or the real path. And of course, as you can see here, the messages exchanged between different agents in the system, between physical agents, digital agents, and yeah, other agents in the digital assets. And this is yeah, the final position of all the robots. As you can see, we have the same, almost the same positions of the robots between the different graphical user interface. And this video shows the exact scenario which has been showed in the previous video, where we had 3 robots and we assigned different destination points for every robots, and here we have a collision situation where the robots started and then moved along the path. So robots can detect obstacles autonomously, but they can detect or collision can be broadcast by using other agent which has information and knowledge about all the positions of the robots. And this is the last robot has moved, and we have shown this in the previous video. So after showing the demonstration videos, here in this slide I would like to discuss some challenges and roadblockers that may face digital twin realization and deployment. The first, from what we experienced, is the low level uncertainty in, for example, the environment and maybe unreliable physical component and hardware performance. And also this may cause inaccuracy and deviation in those physical components. Also, the learning abilities due to, for example, the nature of physical system and the connection between physical and digital assets. So somehow there's a need to real-time systems, and in order to have learning abilities, we have to consider real-time learning mechanisms. And this can be maybe yeah, used by using or storing the data as historical data and use this data as a data set, And of course, the resource capability. For instance, in our case, we will use both digital or cloud service as a container of digital agents, and of course we have the physical components or the edge which uh, deploys the physical agent, and the edge is more limited or resource limited compared to the cloud. So we have somehow resource constraints. And of course, we have another issue, interoperability and standardization. Uh, this yeah, can be solved by using or can be tackled by considering some new standards proposed in the scope of implementing digital twin. And of course, development environment. And still until now, there's no generic development environment and tools dedicated to develop yeah, general purpose digital twins. All those challenges and roadblockers, we have put them in our research, and we try to answer or tackle and address some of those challenges. So as mentioned in the previous slide, here an example of the challenges and roadblockers for deploying and realizing digital twin. For example, we have an extra like investment for yeah, realizing and deploying digital twins in different domains, and of course distributed thinking, interoperability, which has been discussed, and real-time constraints also, standardization, and of course scalability, which can be tackled and addressed by using a scalable approach to make the digital twin more scalable and can be extended according to the new requirements. And also the integration with physical devices, because some yeah, constraints which may impose some challenges to integrate both digital and physical components, supporting technologies and methodologies, yeah, which has been discussed or mentioned in the previous slide. So this is like a conclusion of our presentation, and here we somehow enlist and mention some future work and work under progress. For example, we intend and plan to apply multi-agent learning, and also we will try to consider having more intelligent reasoning modeling, like having belief, desire, intention reasoning modeling in agents. And also we plan to utilize some of technologies that can be used to process big data and a huge amount of data, which generated in real time from the physical components. And also complex event processing can be used to, for example, to detect some deviation or some patterns. And also regarding the interoperability and standardization, we intend and plan to use one of the industry 4 standards provided by, for example, RAMI, Reference Architecture Model Industry 4. And as a concrete example, using the asset administration tool to have interoperable components with Industry 4 technology. Last but not the least, we plan, and this is one of the main intention in this research, we plan to integrate our work with the Flanders Make InfraFlex project, which can provide us more reliable and industry-like environment to have and apply our use cases and case studies and to show the feasibility and applicability of our framework and proposed solution. And this is one of the picture has been taken from the Flanders Make Infraflex project, which belongs to one of the robotic arms that can be used in this project, and we hope to use and deploy our approach in this environment and have more reliable and accurate results. To conclude our presentation here, we are providing some references regarding the agent-based technology, which we recommend to read and have a look about. For example, here there is a really interesting reference about industrial agents and how agent-based technology can be deployed and utilized in industry and manufacturing. And of course, there are another references that can be interesting, especially in the domain of industry and manufacturing. Thank you for listening, and if you have any questions or feedback, please feel free to send us your feedbacks or comments through emails or any other contact details provided